Добрый вечер.
Так, вот сейчас мой этот, джемборд видно, да?
Да.
А вот скажите, я сейчас попробую на телеграм переключить. Увидите вы?
Ну, щас ничего не изменилось.
Ничего не изменилось.
А.
То есть я могу смело
Да,
телеграм смотреть.
видимо, можете.
Сейчас. Я, правда, его сам не вижу. Сейчас. А вот вижу. А вы видите?
Нет, все так же Jamboard.
Все, понятно. Привет. Нет, не слышно.
Добрый день. Слышно сейчас?
Да, 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 теперь
Да.
слышно.
Значит, по поводу следующих семинаров. Значит, тут есть две, ну, не вполне, конечно, по теме, но две возможные вещи. Во-первых, есть такой философ отчасти Андрей Родин, который вроде специалист про Евклида. И
Ого.
мне всегда хотелось узнать, что же именно написано в началах Евклида.
Мгм.
И, ну, есть еще такой Александр Штерн, который в этом самом был в математическом факультете. И у меня была такая идея, чтобы, может быть, их позвать обоих, рассказать, что написано у Евклида, так сказать, ну, вот с самого начала, просто в порядке общего образования. Никакого специального отношения так сказать, ни к чему это не имеет, но просто так.
Ну, давайте, да,
Это
очень
первое.
интересно.
А второе, это вот, значит, ну, как ты, наверное, помнишь, у нас был такой Глеб Новиков.
Ну, еще бы.
Да. Вот. А он потом уехал в Швейцарию и занимался там, значит, всякими этими самыми такими вероятностными науками. И вот он предлагает рассказать про то, чем он занимался, и, значит, ну вот как бы оценка параметров распределения, там все такое. Вот так.
Да,
Но
да,
при
очень
этом,
хорошо.
при этом, ну как бы можно рассчитывать, что он понимает, что мы ничего не знаем, и будет рассказывать понятно, а не как статистики.
Да, хорошо.
Да.
Конечно.
Но это самое, с другой стороны, я не знаю, может быть, есть какие-то более близкие к теме доклады.
Ну, от- я бы еще хотел рассказать про возвращение, но я боюсь, что уже люди так натерпелись, что лучше отложить это.
Нет,
Про
в чем
Евклида.
состоит новейшая теория про замощение?
Новейшая теория состоит в том, что я, во-первых, упростил условия,
Да,
во-вторых, я рассказал доказательства Ромащенко и значит, Андруса, в результате чего получил некоторый опыт, чего надо, можно рассказывать, а чего нельзя рассказывать.
да.
Вот. Ну и, наконец, я понял, что можно сделать то же самое, но для замощений подстановочных. Вот прям как у этого товарища Гудмана Штрауса.
В
Он тоже
смысле,
вот
что не нужно этих условий
нет,
дополнительных?
условия все нужны. Но у Гудмана Штрауса всегда спрашивал я, а вот вы что делаете для подстановочных замощений или иерархических? Он говорил как-то, что и то, и другое.
Сейчас, нет, а в чем разница между подстановочными и иерархическими?
Но любое подстановочная — это любая конечная часть включена в некоторую супертекст.
В смысле, вот, в смысле, подстановка в любом случае есть.
Подстановка в любом случае есть, но каждая подстановка определяет два класса
Там есть такое
значений.
дополнительное условие, что каждая конечная часть включена в одну плитку.
Более
Но это, по-моему, странное условие. Зачем это требовать?
Так нет, это более естественное условие, потому что класс вот просто иерархических, он выглядит, ну там замощения могут выглядеть странно. Вот две, так сказать, совсем разных части можно соединить.
Да.
Да еще и со сдвигом, если мы не требуем сторона к стороне. Вот. А подстановочные запрещают такие странные замощения. Но так или иначе, он всегда говорил, что это не важно.
Да.
Что меня повергало в сомнение, потому что если он говорит, что не важно, то понимает ли он вообще, о чем речь. Оказалось, что это действительно не важно. Удивительно. И вот это я тоже понял, тоже могу сказать.
Да, пока
Наверное,
у нас we just preliminary talk without any specific content, so
without any specific meaning.
yeah. No. So we'll switch to English. It's already time, so we can switch now. But can you share the screen then?
Of course, I will.
No, don't be too fast. Don't jump to the conclusions.
Let me first share also the Jamboard.
Yeah, it works.
What do you mean it works? Can you?
We see Vapnik-Chervonenkis.
No. I mean, can you write?
No. Just
you can.
Yeah.
You can't.
Yeah.
So I will do copy link.
Okay, then I bring the.
Now you can write on the whiteboard, but I don't see anybody on the whiteboard yet.
I don't have my tablet today, so I can.
Okay, anyway. So, Anonymous Kiwi joined. Okay, good. So.
Did you send the link in?
Right.
Yeah, here. Very good.
Maybe it's time to start. What do you think?
No, at least I think we can start slowly.
Okay.
Some people will come later.
Okay. So it's about theorem about CV dimension, proven maybe by Vapnik, as Wikipedia claims.
VC dimension, not CV dimension.
Sorry.
Yeah. CV is different thing.
VC dimension. So I will start not with the definition of this dimension, but with the context where it is used. It's the following problem of learning. We have a known function f from some set, finite or infinite, with binary values. This is our function to learn. And the learning looks like that. So we have some distribution, mu, on the set X, unknown to us. And we have somebody, the learner or the teacher, draws independently some n axis, and this is called, how it's called?
Sample?
Training set. No, training sample or set, training set. And all these samples are drawn with respect to our probability distribution mu. So xi is distributed like mu, and they are independent. That's very important, that they are drawn with respect to the same distribution and that they are independent. And now, the learner, which has these samples and also the value of the function on these samples, so this is called the learning phase. Has to output some function h from x to 0, 1. And the rule he uses might be arbitrary. For example, this might be the following rule. Choose some function h from some set which the best agreement with f on this training set. Or that may be some randomized rule. So choose some h from such set and random, or whatever. We can use some sort of MDL principle, or whatever. It doesn't matter which rule we use for the sample. So we use some rule. And usually one restricts the set of possible outcomes of this training with some set of h of hypotheses. So we will assume that h, the result of the learning, is in some set capital H. H is called the set of hypotheses, and H, small h, is called the inferred hypothesis. So this is the first phase, called the training. And then we turn to the second phase, which is called the test set. We choose another n samples with the same distribution, which is the product again of n distributions. And we see if the learning is bad or good. Again, we measure how we measure it. We consider the number, the fraction of samples in this. This is called test set. In the test set, where we are correct. So this is call it a R test of H. This is the fraction. So there is some noise, Sasha.
Sorry, I just try to switch to iPad, but don't work.
Okay, call it R test. This is the number of i's such that f of x n plus I is equals to h of x n plus I divided by n. The test quality. And also we will consider the so-called training quality of our hypothesis, which is measured in the same way, but instead of the test set, we consider the training set. And a theorem, the Vapnik theorem, states something about the difference between these two guys, the training quality and the test quality. it is very bad, and it's called overfitting if the train quality is much better than the test quality, or in other words, when the test quality is worse, much worse than the train quality. So we are interested in the probability that R train, actually this is R train of H, sorry, not of F, that the train quality, the test quality of the input hypothesis H minus the train quality is larger than certain epsilon, say. And we are to, so to say, frustrated when this probability is large. That means that we infer some hypothesis which is good, which seemed to be good. It had a good coincidence with the learned function, but in
I'm
practice,
sorry, inequality is asymmetric. So we are interested in the cases when test set is much better than train set.
yeah, I write it. It's asymmetric, but it's not important. We can also put absolute value here. It doesn't matter. Actually, I think that if the test quality is even better than the train quality, that's good for us. So I wrote the probability of this, so to say, bad event, that the test quality is.
No, it's not clear. Maybe it's the other way.
This inequality says the test quality is larger than train quality.
Right.
Ah, okay.
Like that, sorry.
Thank you.
The train, it's bad when the train quality is better than the test quality. It's called.
But I don't understand. Then we have some strange strategy. We just choose some function h, which completely disagrees with the training set, and then we are done.
Yeah, all right. And then we are done. Usually one doesn't use such a stupid strategy. Usually one uses the other way around. The hypothesis which with the best coincidence with the train set. But anyway, the theorem I will prove holds for any inferring rule. For your rule, for mine rule, whatever rule you choose, we will upper bound this by some value which depends on the so-called DC dimension and epsilon, some function of epsilon. And this is the Vapnik's theorem. And I want to state it formally, so write the right-hand side and then prove it. First of all, why?
So you say that this is for every algorithm, or
for every algorithm. So for every function or mapping x1, xn, y1, yn into h, for any such mapping.
And for any function f.
And okay, for any function f, for any class of hypotheses, for everything.
no? And so where is the class of hypothesis in this theorem?
In the right-hand side here.
Ah.
Okay, so first of all, why it's not trivial? It's not trivial how one would try to prove it. First of all, we have the law of large numbers, the Chernoff inequality. By this inequality, we know that with high probability, the test quality is just equal to the probability of coincidence. So let's switch to this. So the Chernoff inequality claims that the probability that the test quality of H.
You don't show your picture.
And why? Why is this?
Because you are showing page 4 and not page 3, I guess.
So the probability that the test quality is less than, so let's call it the true quality, R true. The true quality of hypothesis is just the probability under our distribution that F coincides with H. So by Chernoff inequality, the probability that the test quality is less than the true quality minus some epsilon is less than some exponential value of n. To be more precise, minus 2 epsilon squared n, where n is the size of the test set. And so with high probability, we have that R test is actually equal to the true R true of H. For every H, for every fixed H, for every fixed F. So we could argue in the following way. So the test quality is approximately equal with the true quality. And also by the symmetrical argument, the train quality is also equal to the true quality with high probability. So they are equal with high probability. But in this argument, there is a mistake. And the mistake is that the train quality, we can't apply Chernoff inequality for the train quality. That's because the hypothesis H we infer depends on the choice of the samples. For example, we can choose H in our set with the best agreement. And if our class of hypotheses is large enough, then that quality will be much better actually than the true quality. So is it clear?
No, it's not. The entire thing is a bit strange. So what? I'm trying to understand what you said. Just the general direction of the theorem. So in the right hand side, I guess you will have VC dimension, yeah?
Right.
And the theorem says that if we just take if the VC dimension is small, and if our function f and our hypothesis are in this class, then it's more or less enough to get good fit on the test set. That's what you're saying, no?
No. I am saying that this...
On a train set, sorry, train set.
No, what I claim, that if our class has hypothesis has small VC dimension,
yeah,
then whatever inferring rule we have, this probability will be small. That's the theorem.
Yeah, but why what is the meaning that this probability is small? We can be sure the test quality is not much worse than train quality. So it's enough to achieve a good train quality.
Right. You are right. If our class is large enough, so we can choose a hypothesis with a good test quality, train quality, then it's test quality will be also good. And that's very good.
Yeah, because if we consider functions without from a large class, of course we can achieve a very good test quality, train quality by overfitting, and then test quality will be bad. But this doesn't contradict the theorem, because this large class has large VC dimension, and it will be in the right hand side. That's what you are saying.
Right, right. But formally, they are the main achievement of Vapnik and Chervonenkis is this theorem, where we, in all the remaining things that you have said, VC dimension is not important. It is used only this inequality. So the essence of VC dimension is that it upper bounds the probability of overfitting. That's the point I want to convey. So let's first understand what can we put here if we so to say do not use VC dimension at all. So then we can write here the size of the class H times something exponentially small, something like epsilon squared n over 2. And that's because for every specific H, the probability or that the difference is small for every fixed H, while the Chernoff inequality is exponentially small. And since this is true for every H, it is true also for H we infer. And so by the union bound, we obtain this inequality. So this is obvious. Misha, is this clear?
No, I don't understand.
Sasha.
So let me check that I understand correctly. So this probability is depending on several factors, on several spaces. First, we make the train sample. This is one kind of randomness. Then we apply our learning algorithm to get H. This is the second step of randomness. And then we compute all these things.
All right.
And what you are saying now, that we H is therefore depends on all the random bits, but we just consider in the left hand side this event and the fact that this H is fixed. And if H is fixed, that for this specific H, but when we fix H, the distribution on samples becomes skewed. So we cannot say that the training probability is just...
Sasha, we do not consider conditional probability on H. No.
Yeah.
No, we just, let's switch to the next. So do you agree, first of all, do you agree that the probability, I mean, do you agree with this?
Here probability is for fixed H and for independently sampled distributions. Then I agree.
Okay. Misha, do you
I guess Misha also agrees, no?
Yes, yes.
Yeah.
Okay. Then consider our probability. The probability that R test minus R train is, say, larger, smaller, doesn't matter, larger than 2 epsilon, say. Then this is at most the sum of 2 probabilities. The probability, the probability that R test with the minus the true quality is larger than epsilon, plus similar probability for R true minus R train. Right? Sasha?
Yeah, but you want to estimate the event that this R test of H is smaller than R train of H, and H is equal to some specific H0, yeah, and then you want to multiply it by
First of all, you
number
agree
of functions.
Right. First of all, you agree that this probability is small for any specific H. So by union bound, we just upper bound it's by the capital, this number of hypotheses times some exponential small.
No, if you take specific H and some independent distribution of the sample, that's all clear.
Okay.
What should be explained, I think.
The second is small.
No, in the second is also.
So if 2 terms are small, then the sum is small. So
yeah, but
this
is something for specific H.
No, not specific H. Our H depends on the train set. So we use some our H is a function of the train set.
No, if H is a function of the train set, that the second thing is not clear.
Not clear. Okay, I claim that the second clear is that the second term is at most the probability that there is some H star, say, for which R true of H star minus R train of H star is larger than epsilon. And here H star is fixed. So we consider some H star, and for that H star, we measure the quality on our train set.
No,
and also the true quality of that H star. So this H depends on the train set, and this H star is just fixed. And I claim that if the second, if this event holds, then there is some H star for which this is true. So our probability is upper bounded by the union of events. I mean,
I don't understand.
No, let me try to repeat, and then you say whether it's true or not, whether I understand correctly or not. And Misha will check also whether it's true or not. So can you show the previous?
It's difficult to take in mind 2 different arguments. I don't understand the first, and definitely I will not understand the second in this case.
So what's
Okay,
the
but
first and
then
what's the
at least let me say so colleague can check, and then he can say something. So just on page 2, just show the page 2. So there is a probability in the event in the left hand side. This event depends on the test distribution, train sample, test sample, and the choice of H. And then we add an additional requirement in the left hand side, making the event smaller. The requirement is H is equal to H star. And then if we estimate something for the with this additional requirement, when we take union bound over all H stars, and in the right hand side we just multiply by the size of H, yeah?
right?
Now imagine that this event is H is equal to H star additional. Maybe I can even write something. Let me try. And H is equal to H star. And here we delete this. So we need to prove this thing. And then this event is coincides with the event with H star. Because under the assumption that H is equal to H star, it doesn't matter what do we compute. And then H star is fixed, and we have just two n elements samples in the same distribution, and we ask what is the probability that they significantly differ. And this is probability by Chernoff bound, but since we have two samples instead of one, we should divide epsilon by 2, and this explains why we have epsilon square over 2, but not 2 epsilon square n. Okay, sorry for interruption, then you can explain again to Misha, I guess.
But I think Misha should be satisfied now.
No,
Misha?
Definitely not.
yeah. So say it.
I have another problems. I have no problems with epsilon squared divided by 2 or multiplied by 2. It does not matter at all. But I don't understand the whole idea. Suppose our rule is to choose such as that R train is 1. It's possible. Suppose we have a large family of functions, and for any training set, we can choose a function that agrees with all training pairs. Then your inequality says that we are done. On any test, it will be good enough. I don't understand the idea. How
Misha, in this case, the right-hand side will be larger than 1. So the theorem will be just obvious that the probability is at most 1.
Yes, but I don't understand why it's true for any such variance. You can imagine that we don't insist on exact agreement, but take some gap from 1, and why, how it is related with the size of the set of hypotheses. I don't understand. It seems looks Schweik's problem.
So what's the problem? I don't understand. You think that this is wrong? What's your problem?
I don't understand your argument. Maybe it's true. But I don't understand your argument.
So let me erase.
In your arguments, there are no relation. I am trying to explain my difficulties. I see
relation
no
to the size
relation
of-
between the size of. Yes, because when you say that we take some hypothesis H star and do something with it, I
The
don't
size of
understand.
H is here.
Yes, but why it relates to completely different hypothesis H?
No,
In
H,
this-
small h is inside large H.
Okay, and what?
No, so we cannot have too many.
So you
freedom
claim for
choosing
any
H.
H in big H, this difference is smaller than this exponential bound.
Right.
No,
why?
not for any H. No, not at all. This is a statement for randomized H.
What does it mean?
It means that we start with a training sample, then we apply our algorithm to generate H, and then we use this H. So it's a result of randomization.
Yes.
But
I
then,
don't understand how to relate this randomized H with any H.
We can add additional requirement that this random H is equal to some fixed H star. That's what Kolya says. And then we can multiply it by the size of all possible H stars. So if every specific H star.
What is H star?
H star is an arbitrary function from class H.
Okay, for some H star it might be zero, just zero.
Right.
This might be zero, yeah. But if for all H stars it is bounded by this thing, then the entire probability will be bounded by the same times the size of H.
Mm-hmm. And how to prove that for this randomized
with additional thing.
Yeah.
And then what Kolya says, that if we have additional requirement that H is equal to H star, then the event coincides exactly with this event. Of course, because for
No.
they have the same intersection.
No, because you skip the conditions that H is produced by training set.
No.
No.
In the first claim, you use probability for H chosen from the
training set and the internal randomness.
Yes.
But since we added this conjunction here,
yeah,
then it's a very small set now. But this set, for this set, H is equal to H star, because this is just something defined in terms of values of H, and they coincide with values of H star. Inside this small slice, we can replace H by H star. What I tried initially to do is put condition that H is equal to H star, and this is a wrong idea, and Kolya explained me why it's wrong, because this then we change the distribution on the test, on the first sample. But if we just add it as conjunction, not condition, then we can replace H by H star, I think.
Right. And then we will upper
but
bound.
we should remain this term that H star is equal H.
Yeah.
Okay,
so,
Misha, but then we remove it and the probability becomes even larger. And still it is very expensive.
yeah. First we keep it, and then we remove it.
So can upper bound this larger probability, and it's an upper bound for our probability. Okay, I see.
Yeah. So, but this is not Vapnik theorem because there is no
No.
dimension, and
So
this is
it's-
just
it's
some
obvious.
bound which we have here.
It's obvious.
Not that obvious, but it's true.
Okay, it's true, but it's not Vapnik theorem. It's something different. So in Vapnik theorem, we use a better bound, which is usually better, which looks like that. Yeah, in the right-hand side, we use something which is polynomial in n and the so-called dimension. And more or less the same exponential small value. So I won't explain now what dimension, we will see that later. But usually it's much smaller. Sorry. And also this is multiplied by some exponent to n to the dimension also. And usually this 2n raised to the power of t is much smaller than h. So is it clear, I mean, the statement of the theory?
No, so what you write here is just that R training is H is smaller than R test is smaller R training plus epsilon. Yeah?
Right.
No, or minus epsilon.
Plus epsilon. Minus.
Minus.
Right.
R training, R test is smaller than R training minus epsilon.
No, I wanted to write that R test is R test is much smaller, right? Epsilon smaller than R training, right? Like that.
And our test is just not the error probability, it's a
Not the
success
error
probability.
Right.
Yeah. So in this direction, success is in the test is almost the success in the training set. So again, the general intention is that if we have an algorithm which has small, if the class has small VC dimension, then we don't care about test set. We just need to provide a good to fit many test training point. And if we do it, then automatically our small dimension guarantees that for trainings for test set also things will be good. This kind of general ideology of this, what we are trying to achieve, why the theorem is useful. Yeah.
Right. Yeah. Right. Now let's skip to the proof. Let's go to the proof.
Yeah, but maybe you will copy the theorem to this page. It will be better to if we are.
I think it's impossible to copy here in Jamboard.
Yeah. Okay.
The main idea of the proof is the following. We have the product distribution n and another n.
Yeah.
And this product distribution may be obtained in two stages. Stage one, the first stage, we choose the multiset x1, x2n. And the second stage, we divide multiset. Let's call it A. Divide A into test and train set.
No, not only divide, but also select ordering.
Okay, also select order in two sequences. Divide in two sequences. And here we use the fact that all mu's are the same and they are independent. Only under these two conditions, it's possible to divide the generation in these two stages.
Yeah.
Now, we claim that our probability, the probability that R test is smaller than R train minus epsilon is small condition to any A. So condition to A. So it doesn't matter how we choose our multiset. Assume that multiset is fixed, then still the probability will be that small. Is it clear what we want to prove?
So now the distribution is with our fixed set x1 x2n is mixed. Multiset is mixed into n elements, test elements and training elements. And then we apply our randomized predictor to training elements and to test and get H. And then we get some, we apply this, we compute these two ratios for this H. And you claim that this will be small. And because our real distribution on the outputs of mu is a mixture of this distribution, if it's small for each distribution, it will be small for the mixture.
Okay. Now the second step.
Yeah.
Now we want to use the union bound as before.
But you don't say what is VC dimension, and it looks more and more suspicious. You need somewhere to use this.
Right.
But okay, I can wait a bit more. But
okay, wait a bit more.
Okay, yeah.
Okay. Now we use the same trick. We will upper bound the probability. So this is again a union of event. So let's write here the same thing, and that H is equal to some H star, and we want to upper bound by some small quality, by exponential quality. For fixed. But
yeah,
now
and H star is now a function of the value of on A. That's what you are saying now.
I want to say that both are this event for any H actually depends on the restriction on H on our multiset. So instead of the large union with capital H entries, we have a small union. It's only important what is the set of all restrictions of H on A. So here we will have H restricted on A times something exponentially small. And here we will have the same then. And here we don't need to multiply.
No, I think it's better to think like this. H star is a function on A, and you just add the event, this event.
Oh, right. Okay. Yeah. It's okay. And now here we can replace in this part, we can replace R test of H star minus R train of H star minus epsilon and this. Misha, is it clear now? I mean, the plan.
It's not clear, but I see no drawbacks in this argument.
Well, but that's a pity. Here is the main point. Instead of considering a very large class H, we reduce its cardinality to the cardinality of the set of all restrictions of functions from H to a fixed multiset A. So the arguments are just the same, but instead of the large class.
But this set is exponential in N.
I mean, the set of restrictions.
Yeah.
It's not exponential.
No, if we don't know anything about Chervonenkis Vapnik dimension, it's more or less...
restrictions is just a choice of, well, you have multi-set and you should
choose 2n values.
Suppose it's a set. Then actually, how many restrictions do we have?
If we don't say anything, it's 2 in the power 2n.
Yes.
So we need two lemmas.
But then he will say, I guess, that because we know that dimension of H is fixed, Vapnik-Chervonenkis dimension is small, then the restriction, it's not so many restriction on the size of this set.
We need the first lemma that the size of restriction is at most 2n. 2n is the maximal possible cardinality of our usual.
I see. So actually, we repeat the previous argument, but now we are trying to upper bound the set of restrictions by some information about the set of hypotheses. Lemma 1 is a statement about the set of hypotheses, as I understand.
It's kind of main statement about Vapnik-Chervonenkis dimension. It has some name, yeah, I forgot.
Zauer-Schellach.
Zauer-Schellach or whatever, yeah.
So the first lemma is called Zauer-Schellach, and the second one is just, I will prove the second one first. So our statement follows from these two lemmas then.
But the second one you already explained.
And in lemma 2, H star is arbitrary.
No, it's not independent now.
No,
just...
H star is just some function for every function H star from A to 0, 1.
So we're not in the exactly in Chernoff lemma case, so some additional work is needed.
Yeah. So I will start with lemma 2, which is simpler than lemma 1 and more or less obvious. So proof of lemma 2. So let's consider the picture. So we have some H star, which is fixed. So H star divides the whole multiset into sets, good and bad. Good when H star agrees. So good means H star agrees with F, and bad. And say say here we have say say P, the fraction here is say P times 2n, and here is Q times 2n, so that P plus Q is 1.
But sorry, just let me ask. So it's you are proving some result in probability theory, and the result of probability theory is that if you take a random set of given size, and put it in subset of given size of 2n element set, that with high probability the fraction of elements in the first half and in the second half will be the same.
Mm-hmm.
That's what you are proving.
Right.
You can forget about this H, this and this is just that there are kind
So
of...
I just wanted to state it. So we have some good balls and bad balls, and P is a fraction of good balls, Q is a fraction of bad balls. Now we choose at random exactly n balls in the training set and another n balls in the test set. So this on average there should be also Pn good balls in train set and Qn good balls in the bed, and so on. So we expect that here we have Pn and here also Pn, here Qn, and here Qn. This is on average. And we want to estimate the probability that here we have, say, greater than P plus epsilon, and here is less than, so hence less than P minus epsilon. And again, here is, because the total is n, so here is smaller than minus epsilon plus Q, and here is larger than U plus epsilon n. And we want to show that the probability of such events is very small, exponentially small when as n increases. And probably there is a theorem about exactly this setting, but I don't know such a theorem, and I want just to reduce this to the case when division is not exactly as n, we just divide the whole multiset into two sets at random. So each point is chosen in the, say, train set with probability 1/2. So, and I want to show that first, by the law of large number, this probability is exponentially small, and second, that our probability is close to that one if we neglect the factors of which are polynomials in them. So in our lemma, so assume that instead of instead of the probability. So now the only source of randomness is the division of multiset into two halves, n and n. But assume now that instead of we change the probability distribution, we consider just the uniform distribution. So each point is chosen with probability 1/2 as a test point. Then our probability, the probability with respect to uniform of the same event, conditional to the event that the division is 1/2 to 1/2. So n exactly n balls are test ball are in the test set. All right. And this is this conditional probability is at most the probability of our event over the probability of the condition. And the probability of condition is proportional to 1 square root of n. So it's large enough. And now we just need to upper bound the probability that with respect to uniform division, there is the average deviates by epsilon over 2 from the expected. Because you see, if this is less than u minus epsilon and this is larger than u plus epsilon, then the deviation, the deviation of the real fraction of chosen balls from its average is at least by epsilon over 2. So because we expect the fraction q, and here the fraction is q minus epsilon, and here is q plus epsilon at least. Sorry, we expect q over. Yeah, we expect q, and so this probability is at most that much e to the minus the number of tests, the number of trials over epsilon over 2 squares, and the number of trials is at least n, because either we choose the lower half, the bad balls, or the good balls, depending on what is larger, and we obtain this bound. So I am finished. I mean,
no, it looks suspicious. It's a kind of do-it-yourself argument for probability theory, but just for explaining that independent choice of each bit is more or less the same as choosing one subset of size n over 2 in case we are interested in fractions of this bad and good elements. But maybe it's kind of some.
It's a sort of exercise in probability theory. It's rather clear that it's true.
Yeah,
There are no
I guess it's even true without the
place.
square root of n, or
maybe
that should be true.
Square root of n is about the size of the largest slice in the Boolean cube. It's quite clear. But
I guess that the more professional argument will not give 1 over square root of n, but one should think about what this more professional argument is.
You suppose that you can do better than...
No, I guess one can at least try to apply a Zoom inequality and see what happens. And I get something.
I'm not sure that the result would be significantly different.
No, just the square root of n thing. Okay, it's not important, but I just my bet is that experts could say that this square root of n is not needed and explain why. And maybe assuming inequality is sufficient for that, but I should think.
Maybe, I don't know.
Yeah.
Okay, so it remains to explain what is a DC dimension and how to prove Sauer-Schalag. Right? Okay.
Yeah, I even I heard it 10 times probably, but I guess what I remember is the VC dimension is just at the maximal size of subset on which we have all functions. Or maybe minimal size of subset of which you don't have all functions.
No, the maximal. So the definition is like that. So VC dimension is defined like that. So we have H, the class of functions,
on X
with binary values. Certain class H. At definition, we say that H shatters some subset A of X if for every, say, G from A to 0, 1, there is a function H in capital H, which agrees with G on A, such that G equals to H restricted to A. So all possible functions, all possible 2 to the capital A functions can be realized by some hypothesis from H. And the maximal and VC dimension of H is defined as maximal size of A, such that A shatters, H shatters A. So this is the definition of the dimension. Now, Sauer-Schalag lemma 1 claims that for every A subset X, if we restrict H on A, then we have at most the following sum, the sum of binomial coefficients, A choose I, where the sum is from 0 to the dimension.
But A is not that A. We can just forget about A actually. We can just say if X just get this.
Call it S.
We can just get what we want to show. It's a bound for the size of H in terms of dimension and size of X. But of course, when we restrict our H to some subset, dimension doesn't increase. And so
why do changes A by S?
no, because A is now used in the lemma.
Because on the previous
But
page,
another version
has another
was to
meaning.
note that it's enough to show for the case when A is equal to X, the lemma. Because we can always restrict everything to A. and dimension becomes only smaller. So, but we can do both.
So our lemma 1 follows from this lemma 1, because the sum can be upper bounded as the dimension plus dimension plus 1, the total number of terms, and here and these binomial coefficients may be upper bounded by so in the first case it is a to the I, that is a to the dimension. Dimension plus 1 times a to the dimension. And in our case, the size of a was 2n, and we obtained dimension plus 1 to n raised to the power of the dimension. So
it's d plus 1 n over d, the notation which was used there.
d plus 1 to n to the d.
2n to the d, yeah. There was exponential part and not exponential part, yeah.
The polynomial part is dimension plus 1, and this is the exponential part. And this is proven as follows. First, we prove an auxiliary statement. So auxiliary statement is like that whatever h we have, h shatters at least the size of h different sets. Instead of considering the maximal size of the shattered set, we here consider full shattered set, whatever size they have, and we want just to prove that there are many of them. And this auxiliary statement easily applies the lemma. And that's because by this auxiliary statement, we can upper bound h by the number of set it shatters, h shatters,
and it doesn't shatter big set, and then we get.
And once we know, first of all, we consider, probably you have already said that first we restrict our set of hypotheses to our set A, and certainly this restriction doesn't increase the dimension. And then once we know that the dimension is not increased, and then know the maximal size of the shattered set, we can just upper bound this by the number of at most g element subsets of A. And that's what our binomial sum of binomial coefficients provides, just the upper bound for this set. So it remains to prove this auxiliary statement. And this is done by induction. So the proof by induction.
Sorry, I missed something. why the number of sets shattered by H is less than the element subset.
Because we assume that H doesn't shatter big sets. So it can shatter only small sets. And here
There is
VC dimension.
maximal
Size of the sets that can be shattered.
Okay, yeah.
So, and this is proved, I mean, this auxiliary statement is just proved by induction. So, by induction on the size. So, base of our induction is when the size is 0. That is, H is I guess not.
Oh, it's a kind of trivial for H.
No,
H.
H is 1. H is 1. Sorry, H is 1. So we need to find a set which is shattered by H, and this is the empty set. So shatters the empty set because for the empty set there is only one function we need to realize, and this function.
Yeah, okay, yeah, it's kind of.
So induction step. So assume that H is at least 2. And we know that the statement is true for all smaller H's. And then we fix some element, A fix some element, and fix
Of our element of H or element of the set?
Of the set, and two functions, A0, which is 0 on A, and A1, which is 1 on A. And there should be such functions because we have at least two different functions. They differ on some element, and A is chosen as the element where they differ, and these functions are also fixed. Okay.
So A is not arbitrary, but still.
It's not arbitrary.
Yeah.
First we choose different functions, then we choose A. And then we divide our H in H0 and H1. Actually, this is a partition where H0 are all functions which are 0 on A, and H1 are all functions which are 1 on A. So H0 is small h0 in the capital H0, and the same for H1. And then by induction hypothesis, we know that there are capital H0, because both of these sets are smaller than H, and we can apply hypothesis. So we have induction hypothesis for both of them, and we have already this much and this much shattered set. So of course, when we increase the set of hypotheses, we increase the number of shattered sets. So we have this and this. So we just add them, and we obtain that much shattered set in total. But unfortunately, they may intersect. It might happen that some function is shattered by
Some set.
Set is shattered by both H0 and H1.
Large H0, capital H0 and capital H1.
It might be like that. So these are sets shattered by H0, and these are sets shattered by H1. And here is a set which is shattered by both of them. So it is counted twice. So we need somehow to find this much new sets shattered by H, which were not counted before. So for every set in this intersection, we need to find the new set which is also shattered. So how?
But it's not shattered by H0 and not shattered by H1.
Right. A new shattered set, which is neither shattered by H0 nor by H1. And this is done as follows. So we just take any set of from here.
So you some H or what?
So let's call it, say, S. Let S be some set from the intersection. We consider S union A. First of all, A can't be inside S.
Because H0 is fixed on A, so any subset containing A cannot be shattered by H0.
So this is indeed a set which is outside both H0 and H1, because by the same reason H1 can't shatter this one, because all functions from H1 are 1 on this element A. So this is indeed a new set. And also it can be shattered by H, because if if we want to realize a function which is 0 on A, we can use some function from H0 which realizes that function, and otherwise from H1. So this is a new set which is shattered by the union. So that's the induction style.
Yeah. So I remember that somebody already explained this strange argument. It was indeed easy, but very strange why it happens. And there is another, even more strange argument of Roman Smolensky, who considered polynomials and without induction, he just. But I knew it once, but now I cannot remember it. But it's also extremely simple.
Misha, is it clear? I mean, the proof.
To some extent.
Okay, very polite.
I can ask a question. Look, you take small a, you have some h, okay, and you take a and two functions. But why does a do exist?
Because we first take two functions, two different functions.
Yeah.
We assume that our set has two different functions.
Yeah.
Being different, they differ on some element.
Okay.
And we choose that element as A.
So if you need, you just swap H0 and H1.
Okay.
Okay, I see. And the next question is about this set S union A. You explain that it is shattered by H, yes?
Mhm.
So if you take any subset, take a subset that contains A and something from S.
Mhm.
What is the function which from H with these values?
Okay, S is shattered by H1.
Yeah.
So there is a function which is agrees on our function on S, capital S,
Yes.
from H1. And this
Mhm.
function takes the value 1 on A because all functions from H1 have that value on A. So,
I see. I see. I see. Okay. Well, so I hope that I understand this induction.
No, the other argument somehow, if we take any function and try to represent it as a polynomial on this value, part of Boolean cube, and since I think that since it doesn't shatter big sets, then it means that there is we can replace big polynomial terms by smaller ones, but that was something like this. And I think we already discussed it maybe several times, but sorry, I am completely sclerotic now, so I forgot how it works. Yeah. But this argument also is simple. And probably we also discussed it, but or maybe at least somebody explained it to me, but and probably many times, but
mhm. So I think we can stop here.
yeah, okay. But what about the next time? Maybe some of the participants wants or know someone. I have some plans, as I explained. One of them is very strange. No, both are very strange. One of them is to ask Gleb Novikov, who was working in ETH for being a graduate student, and they studied some kind of probability theories, guessing distributions and separating. So we have, for example, a normal distribution and two normal distributions mixed, and wants to find parameters of both or something like this. There is a huge theory about this, and they achieved something. And he is ready. He was ready at some point. I hope he's still ready to explain what is this field, what is this domain, what they are doing, and what it's all about. Something elementary. And another completely different topic is there is Andrei Rodin and Alexander Stern, who seem to be somehow experts in history of mathematics. And I always wanted to know what is written in Euclid Elements, and maybe they can try to explain something about this. Just a kind of complete digression, but maybe some people want to give some more directly related talk. Kolya, maybe some of your students in Moscow University or in HSC want to tell something.
I think so, but it's, I mean, Timur Kuptsov would explain his master thesis, but that's very technical actually. So I
And who understands it? Do you understand it already?
yeah, I understand it. So that's not very interesting. That's the problem, because it's first of all,
It's bad.
it's technical and also very, very special. So let's postpone his talk until we hear more sensible talks, so to say, more understandable talks. So, but better to start with Euclid, I guess, because it's sort of
Okay, but that I should ask, because I did not agree about any specific time. I just discussed this in general.
And
But
I'm sorry about Euclid. How you imagine this talk? There are, as I remember, there are 14 chapters in the Euclid book. And what the talk was, the first chapter is blah, blah, blah. The second chapter is blah, blah, blah.
I can tell my own impressions that I try to read the first chapter only. And then just as imagine, not as in a historical position, but just
in Greek. You have tried.
No.
to read
I
it in
asked
Greek.
what is the translation, and there is a Russian translation, and there is an English translation, and the experts say that they are more or less close. So there is a
To the
traditional.
original.
No, there is not such a thing as the original. There is some Greek edition of Euclid reconstructed in 19th or 18th century or something like this.
Oh, so actually, Euclid book was written in 18th century.
No, it was based on some. No.
The ancient town of Efes in Turkey was built in my eyes 20 years ago.
Yeah. No. But no. It's no. Seriously, I don't think they definitely try to. They don't write something in Greek. They don't know Greek so well. They try to compile something from different sources that were existing at that moment. Of course, there were first editions in six. After it was introduced in Europe and so on. But what is completely strange for me, I don't understand why they prove something and why they don't prove something, and what are the notions, and just the entire thing looks completely strange, just from the reader point of view. So if I imagine myself as a student, I would be quite confused. What should I prove and what should I not prove? And how I should prove, and what is allowed and what is not allowed. It looks like something very, very ridiculous. And I guess that there should be some internal logic, at least on the level of course, it's not a formal theory, but students probably have some idea what should be proven and what not. And that my idea was that maybe experts can somehow communicate this intuition. This was what, but this is very. Of course, it would be better if people read try to read in advance. Maybe it's me who don't understand what they are doing, and other people could do this. So it's quite possible, because
I've read not the first chapter, but the first 2 pages, and my impression is quite similar to you. I don't understand the style, and actually I see no need to understand it, because well, it's Euclidean geometry. We know how to claim geometric facts, how to prove them. You can try with Magnitsky arithmetic, maybe. It would be, I guess that it would be as unclear to you as these Euclid books.
No. Magnitsky arithmetics is just kind of very randomly chosen textbook, okay. But Euclid seems to be very, very significant in the history of mathematics. So during many centuries, people believe that they understand that. So I guess they have some internal logic. No, of course, now we can consider two-dimensional vector space over R, and that's all. But no,
Do you know what is Sponsa Sinorum?
I forgot. Maybe that's something.
It's a theorem about isosceles triangles. If angles are equals, then the corresponding sides are equals in the triangle.
No, I think it's if sides are equals.
I'm not
No?
sure. Maybe if sides are
No,
equals, then
actually, this is just one argument. In Euclid, it's ridiculous completely. Still,
this theorem considered as a very difficult result.
Report that first I tried to read it, and second I understand this argument on the level of high school geometry. So it's very strange, but it does some additional construction and so on, but it is not the place when I'm completely lost. Okay, I acknowledge that the author may have a strange proof. Okay, this is not the problem. The problem is that I don't understand what he wants to be in the proof and what he doesn't want to be doesn't need to be in the proof. Okay, so just that's what it is. I don't know. I don't claim it's interesting, but
it's slightly exotic exercise.
Definitely exotic. Definitely, it's very exotic.
Reverse engineering of formal system when there are no formal system at all.
No, it's history, of course. It's not.
It's not history. Euclid did not have a clear picture of formal argument, of a proof. It was some preliminary version of it. And of course, if you, with your high standards of rigorous proofs, try to reproduce Euclid's argument, you have some problems.
No. It's not exact. It's completely different. It's not what I wanted. Of course, I understand that it's not rigorous, nothing like this, and so on. But I just want, in the role of a high school student, I want to understand what they expect from me. For the high school geometry, it's all in the modern version. It's also, of course, they always say that this point in this, they don't explain why the point in this region and why they intersect and blah, blah, blah. But then,
Sasha, Maria Ivanovna says, what should you do? It does not matter.
okay, but I can, what I'm saying, that I can simulate Maria Ivanovna, but I cannot simulate Euclid. I understand why, what should be, what is expected from modern high school geometry, and in Euclid it's very strange.
Sasha, my remark is, when you say you cannot simulate Euclid, you mean you cannot simulate an abstract Euclid, which should be extracted from the text written in 18th century based on some ancient books, and the origin of these books is some tradition of education in ancient Greece, when books were not the unique way to fix knowledge. There are many oral communications between teachers and students, and you cannot extract these communications from nothing.
Whatever was in Greece, in Europe for many centuries, starting from Euclid and ending
in Europe, Maria Ivanovna is a very good approximation.
Not really, because for the textbook which are written in the end of 19th century, like Adamar, this is not a problem. But people actually read Euclid and somehow understood it. Anyway,
Okay, yeah.
if it's not But
It's interesting attempt, so let's try.
the best solution, if maybe you have something to tell, or some of your students, or just it definitely has no relation with our main topic of the seminar. It's kind of a digression, just for fun, if we don't have anything serious. So, but if we have something serious, or some of your students, for example, in last semester we have something extremely serious with this cat and ant story, which I hope finally will converge to some paper. But
Cat? Sorry?
no, it's Danish students who studied cat and mouses in complexity. But maybe somebody has something to tell. Some of your students did something and they are wanted to.
I'm not
Okay,
sure.
let's think. I will ask people about, maybe they just cannot give a talk next Monday, or what they think about this, and then and you may think who else can be speaking. There are many people in HSC, and some of them probably are doing interesting things and so on.
Actually, I have a session at HSC, not next week, but 2 weeks.
And the
after
student
2
also
weeks.
will have it.
Yeah, but well, it does not matter.
Okay, so just if you or Kolya have some people in HSC, then it's also a good idea to ask whether they have something to tell. Okay. So if nobody wants